Hi everyone, we're going to look at the credit distributions and we'll look at graphs and statistical tests. So the graph we're going to use is called the population pyramid. If you're a biologist or a geographer, you have seen these before. The horizontal axis is the percentage and it's on each side, and it's like a mirror line. They're reflected on each other so we can contrast each level. 12 to 2016 on this side, 2017. The vertical axis shows us the external credits. So working from the bottom, these two lines going out to about 20%, about the same length, at 0 credits. Then at 4 credits, they're about the same length. Then at 6 credits, they're about the same length. Then we get to 10 credits, and we can see straight away that the 2017 bar is much, much longer at 40% than the 2012-2016 bar. And then for the, what's that, probably about, about 12 credits, the blue bar is slightly longer than the red bar. And then we get up to the very top at 16 credits, we can see that the blue bar is about 45% versus the about 25% on this side. So the longest bars for each of them is called the mode, the most frequently occurring, and in terms of shape, it's called the peak. And so for the 27 distribution, we can see the peak is down here at 10 credits. And for the 2012-2016, we can see the peak is at the top, which is a good place to be at 16 credits. So it actually looks like the 2017 distribution has earned less credits, which is not the best. So let's just scroll down to, now I then give you the averages, and we're using the median because the mean average can be deceptive with credit distributions. So we use the median, which is the middle person. So the middle person for 2012 to 16 earned 12 credits, and the middle person for 2017 earned 10 credits. If we scroll down to our statistical tests, we can see you get this lovely box. The important thing is the significance here, but that just basically tells you the null hypothesis, which is the assumption that everything is the same. It tells you the name of the test, which is the Mann-Whitney-U test. And then the significance, this is the probability that any differences are random, and this is quite a low probability, 0.074, 7.4% chance that the difference between the two distributions is a random occurrence, just from year-on-year variation. So you get your three options, and in this case, the p-value, the probability is, if it's greater than 0.10, would say it was similar, but that's not the case. In this case, the p-value is less than 0.10 all the way down to 0.01. It falls into that range. So this is the one we choose. So we say the 2017 year, where it had a median was 10, is notably less in this case than in previous years, where the median was 12.0. This gives a p-value, a probability of, oopsie daisy, 0.074. There's only a 7.4% chance that the difference between those two distributions is random. Now, that doesn't sound good for physics, so let's now scroll down to internal credits, and we might see something a little bit more positive. So we'll look at the internal credits earned. Now, straight away, the graphs are full of visual impression. And straight away, we can see that the peaks, okay, here are the peaks, all right, and they're in the same place, but the bar above it for 2017 is much longer, much longer than that. So 25 or 30 odd percent, 30% of the students got 10 credits in 2017. Whereas, and this looks like the distribution is pushed up in comparison to this one. So I would expect that yeah, there might have been an improvement in the internals. So let's scroll down, see what the medians are. The medians are the same. Isn't that interesting? So the median is the same, but what does the statistical test say? So this is an interesting one. The statistical test gives you a significance. The chances of that happening, even though the medians are the same, the chances of that result happening randomly are less than 0.001. It's so small it doesn't register anymore. So the chances of that happening is virtually nil. So even though the medians are the same, the distribution is better. More people got those higher grades. So we go to this one here. The p-value is less than 0.01, so it's significant. So we would say, and this is quite a strange thing to say, I suppose, in a way, the internal credits earned in 2017, although our median, which is 7.0, that's the middle person, is significantly, I would say more in this case, I would say better. I'll change that more to better, because the median is not more than in previous years. So I've got a 7.0 and the p-value of, now we don't write down 0 because it's not, but we just know it can't be registered on that scale, so we put less than 0.01. Oh, and 1.02. Right. So the internal credits earned are, and I suppose my syntax is bad now, are significantly better. I could even make the sentence even nicer. The distribution of internal credits earned in 2017 is, now it's back to this again, is significantly better. There you go. So scrolling down, that's now so what happened overall? Total credits. So here's total credits earned. Right, just looking straight away. Here's my mode, my peak, and here's that peak there. So the peak of 2012 to 16 is still higher than the peak of 2017, but I've got that bulge at the top. There were 15% of the students got 26 credits. So is it better or worse? What's happened when you combine the internals and externals? So let's scroll down. Oh, look at that. The medians are now the same. The medians are the same again, just like it was for the internals. And look at that, the significance value. So the chances of that distribution happening randomly is 77.4%. Yeah, there's no difference between the two distributions. So we'll go down to here. The total credits earned in 2017 is similar. So what was it? Median. What was it? 17. Both of them. Just check that. 17.0. Yeah, it was. And the p-value was 0.774. That was right, wasn't it? Yes. So they did worse on the externals, better on the internals, and overall the total credits earned similar. There's no significant differences.